Okay, cool. Hello, guys. Welcome, everyone. I guess they can see that, right? They can see up to here. Cool. Up to here. Nice. All right. So, welcome. Today we'll be going over the security badges problem that Giri gave us. It's from ICPC 2017-2018, Southeast Regionals, I believe. I put the problem in chat and description of the live stream in case you guys want to read it, but I'm also going to be going over it right now. Yeah, Southeast Regional Contest. So in case you guys don't know what that means, let me bring this back up. So ICPC competitions held with other schools, and then this wasn't one of the contests. This problem was one of the contests in 2017, 2018 in the Southeast Regional. And now we're going to get into it and try to solve it. So what is the problem? Problem says there are K amount of badges. There's certain people that have badges, and there's certain rooms, and there's certain doors. You are told by your boss to find out how many people can get from one room to the other, from the start to the destination, with the badge they hold. Each room has a range of badges they would accept. So they have a minimum range and they have a maximum range. So let's say my badge number is 42, and the door I'm currently looking at has a range between 10 and 100. I can get through that door because I'm between the range. If my badge was 200, I cannot go through it. Once you go through a door, you cannot go back out of it. I should probably draw a map here so it's a little bit easier to understand. Okay. Yeah, let's break this. There we go. So here we have N represents the number of rooms. So we have 1, 2, 3, 4, 5, 6, 7, 8 rooms. We will say that our start, let's call this our start right here. And then our destination is this one in the bottom right. Then, of course, each room has a number of doors. It tells you specifically which room has how many doors in the input of the problem, but I'm not going to write out that input. I'm just going to tell you that, let's say this door has 2 rooms. Oh, sorry, this room has 2 doors. This room has 1. There we go. So this represents the doors. Then each box is a room. So this is the input they gave you, and the description as well. They make you see it this way. But of course, this might be a little bit hard to understand. There might be a better way that we can represent this problem. Does anyone want to take a shot? How can we represent the rooms and the doors? Okay, a matrix is not bad. Yeah. Is there any other data structure? That answer is like. Not hash table. Something that uses nodes and edges. Graphs. Yeah. Exactly. So yeah, your answer was also right because you do use a adjacency matrix to represent this. So yeah. But I was trying to get a graph out of you. All right, cool. So let's say each room is a node. So this one is a start one. Let me color it S as well. Then we have another one down here. Then we have another there. Cool. And this is our destination node. Now, remember how I said that the doors, once you go through it, you cannot go back? What does that tell you about this type of graph?
Directed?
Yeah, that it's a directed graph. Okay, so this one can go to this one. Say that. Say this. Okay, cool. So let's say our graph looks like this. This is saying this edge right here represents this door. And since it's directed, it's saying that we can go from here, from this room to this room, and we cannot go back. Perfect. So we now know how to work with our input, which is really important. We no longer have to worry about something that looks like this, and we can actually use a data structure that we're familiar with, which is a graph. But for now, let's take a look at our inputs. There's one very large input here, which is k. And let me repeat that k represents the number of badges that there are. K could be greater than or equal to 1 or less than or equal to 10 to the 9, which I think is a billion. Yeah, I think so. So this k could be very large. This means that depending on our algorithm, we might run out of time, and we have to be very careful. So just by looking at this, to get like a general idea of how we would solve this, what do you think would be a good solution?
Well, I guess where I'm lost is we still need that number with which we know if we can go through that door.
Yeah,
or
yeah.
not. We're missing out part.
So the range, is that what you're talking about? Okay, yeah. So that's a okay. You caught me. Okay, yeah. That's a very good point. Each and every single one of these edges, since they represent a door, that means they have some value to them as well, which is that range that they give us. So let's say A and B, C and D, E and F, then so on and so forth. Let's say now for each and every single edge that we take, we do know its range. I only wrote a couple of them. You can fill in the rest in your mind. But with this information, since now you do know that each door has a range, how can you try to figure it out? How can you figure out how many Ks or can go from start to destination? Yeah.
So these are like persons?
Yeah, it's the number, you can think of it as people. Like each badge represents a person.
So like check if each person is within the ranges, and if it is, you can go to the next node.
Yeah. Yeah, so that's a good naive idea of it. And just look at all the people and see how many people can go through them. Do you agree that there might be multiple paths to the destination? It might not just be one? Yeah, so we want to check that as well. So we want to look at each and every single node and see if it reaches the destination. So by saying that already, we already know that we need to use some sort of graph traversal algorithm.
Does it have to be the minimum path, or just like any path?
It can just be any path. We want all the paths actually, because we want to know how many people in total can go from start to end. So we know we want to traverse this and try to hit each and every single node and see how many can reach the destination. Your idea was good, but then when we look at our input and we notice how k is 10 to the 9, we realize that it might be way too large and we might run out of time. So it might be slightly better way of doing this. And it relies on looking at the ranges. So let's say we have 1, right? Yeah. So let's say we have a number line that represents our k. Crap. So we can use this number line. Let me make sure they can see that. They could, cool. We can use this number line to tell us multiple things. First off, represents all of the badges, but it can also show where our ranges are at. So for example, this A and B, A could be here, and then B could be somewhere over here. You agree with that so far? Yeah? Okay, cool. Now let's look at C and D. C could be somewhere here, and then D could be somewhere here. All right, cool. We're still agreeing. Now let's look at E and F. E can be somewhere here, and then F somewhere over here. Right? Okay, cool. All right. Now, with this information, how can this help us?
We just need to look at the minimum and the maximum, or everything in between?
Everything in between? Yeah. So we know we don't have to worry about these, right? That's what you're saying?
Yeah.
Yeah. So that's a very good point right there. We already know that we can potentially discard a whole bunch of them. Let's say this last one up here has a value of 1,000. And since we're going all the way to 1 billion, there's a whole bunch of numbers we've gotten rid of. But let's say there was a door that has a range of 1, a minimum range of minimum value of 1, but a maximum of 10 to the 9. How many values do we throw away now? Yeah, so we don't really, there's nothing greater than this, because that's the maximum. There's nothing lower than this, because that's the minimum. So we still have to consider everything in the middle, because all of these values could still reach D at some point. So there's a special trick here that Dr. Giri mentioned. Do we really have to check each and every single value?
Are they sorted or something?
Okay, they could be. Yeah, that's into the code. So yeah, that is part of the answer. We would want to sort this later on, initially. But let's say we did sort it, and let's say these are all sorted already. Do we have to go from, let's say k is 10 to the 9, do we have to go from 1 to k to the 9 and check each and every single one? Let's say we take one value, right? Let's say our k is equal to 13. How can we tell if this k can reach the destination?
We have to make sure it complies with 2 different ranges.
Yeah, so we have to make sure they can get through all the doors for every single ranges of the doors and reach the D, right? The final node. So if we're starting off here in S and our k is 13, give me a general, very general algorithm of how we can figure out whether we can reach a destination or not.
Well, okay, so I'll have to check if 13 is between C and D or A and B.
Yeah.
And then, depending on which one's true, I can go to the next one.
Yeah. Yeah, exactly. So look at his children, and let's say this, the children of S, this one right here. If K is between the range of A and B, let's go to this node and continue looking at the children of this node. And we also want to do that for C and D. Let's say for C and D and A and B, 13 is in between. So now we're looking at it here and here. Now we want to look at the ranges for E and F. And then for this one's not labeled, but for this edge as well. And try to get to all of them and see if there's one of them that reaches D. If there is, then we know that K is equal to 13. This is valid, and we could reach D. So this is potentially one person right here who could get from start to the destination. So going back to our number line with these ranges laid out for us. Let me delete these because there's two blacks. For this first range right here, let's say this is 7 and then this one's 20, right? If we choose a number in between and then check with that number and that number passes, do we have to check every other number?
What do you mean with every other?
So let's say we get the middle number, right?
Okay.
Right here. Let's call this R. So that's number R, right? This is 7, this is 20, let's call it R14 or whatever. I don't know if that's in the middle. Can't do math that quick. Let's say R is equal to 14.
Okay.
Oh, look, it's one higher than K. And then we send R to our graph. We check if R can reach the destination. If it could, let's say it could reach the destination, do we have to check 15, 16, 17? And do we have to check 13, 12, 11?
Yes, because for some other door, that range might not work.
Okay, good. But here we have the ranges for the other doors, and they don't overlap with this one, with the black ranges.
So again, it's hard to block.
Wait, actually, that's a pretty good question. Give me a second. Hold up. No, that should still work, right? Okay, cool. So let's say our, in this example, cool, yes. Okay, let's continue. In this example, if we don't look at this up here, when we look at the bottom, R would fail. It would fail because the other doors have a minimum that's greater than the maximum of this black one. So we know that if this R fails, all the other ones will fail as well.
Right.
Let's say that's not the case. Let's say this blue, instead of being in front of this, of the max for the black,
Okay.
it was behind it. Then we can erase this one.
The intersection of all the ranges?
Yeah, it's exactly that. Every single intersection we want to check. So, okay, you already got the answer, but let's say pretend you didn't say that. Okay. In this case, there could be a route that reaches D, because now we have two doors. If we check with 14, then 14 is most likely going to go through the door that's blue, right? It would be the same thing with 15 and 16. So if 14 passes, we know that everything in here would pass as well. If that's not the case, or if it's not the case, we know everything fails and we don't add it. If 14 does pass, then we can add the difference between these ranges. Again, let's say this is 7, this is 20. That's what, 13? Yeah, I think it's 13. If 14 passes, then we can add 13 people can reach D. That part makes sense?
Consist of the number of people?
Yeah, the number of people, number of badges, they're really the same thing. Hello, Joseph. How did the Google interview go? Confidential? NDA?
The NDA.
Okay.
Actually, I won't talk.
What? You told me you won't talk about it at all because you signed the NDA? I totally respect that. Okay, thank you. Okay. That's a lot to go over. But
I was looking at it a little bit because I was in the live.
okay, cool. Thank God. Because, yeah, we're pretty deep in already.
It's like they can only go in a certain path, right?
Yeah, so directed graph, yeah.
Yeah.
Okay, so let's say we already know this is most likely not going to pass because every other door is minimum, unless there's a straight, unless this black range is from S to D exactly. If that's the case, then we could potentially add all these. So that's why we still want to check it. That part makes sense, right? Like a direct edge. Okay, cool. For all these other ones, you said this already, but it's the intersections between them. We don't just want to look at the middle of blue and blue. We want to look at this value and then the next closest value. So now we want to look at this range right here. And we want to test that the exact same way. Now, I believe this is something that I overlooked and I don't think I went too deep into it. But if we have a value and we want to test to see if we can get from the start node to the destination node with that value, what type of algorithm would we use? Any one of you guys? BFS? DFS? Okay. Any other? Yeah. So yeah, you were totally right, and you're also right. It's both algorithms. Really doesn't matter, as long as it allows us to traverse it. It's fine. So yeah, we want to take the middle value between these two ranges, and then use DFS or BFS to see if we can get from start to end, while taking into account the ranges of each edge. Let's say this value is outside of this range, but that means that we never consider this edge, and we only go down this one if it's within this one. So that part is pretty simple and straightforward. And then with this algorithm, if we were to do, like you said, sort these ranges and take the intersection of each, for each intersection, we find the middle value of that intersection and then test it. With that value, if testing that value comes out to say true or positive, whatever, saying that we could reach the destination node, then we want to add the difference between those two. So the reason I say the difference is between this first value could be 20, the second one could be 35. How many people are in between? 15. Or how many badges are in between? 15. And then we add that value to our answer. And that's it. That's this problem. As you see, it's not really like difficult, right? It's algorithms we know. We know DFS, we know BFS. But it's really just a strategy of how we can work around this K. We know our K is extremely large, so we most likely won't want to be using that. we want to use a smarter approach, which is sorting it and then taking the intersection and just checking the middle value of each intersection. If that middle value passes, then everything within that intersection will also pass. So it's just kind of a way of thinking of it and working around it so it can be efficient and work within our allotted time. So since you guys said BFS or DFS, let's go with BFS. What's the time complexity of BFS?
Versus the
Wait, what?
log n.
Log n? I don't think so.
Wait,
BFS?
what is the input?
It's a graph.
A tree?
It could be a tree, could not be a tree.
Like a matrix, like a 2D array?
Wait, what?
Like, is it a 2D array which goes in, or like, so
Like the input?
yeah, then
No, it's just be like pair of numbers. Like let's say like room number 4 has a door from that goes from room 2 that goes from room 4 to room 2, something like that. It's not really like a table. It's much weirder. But you can still work around this. You know that if you build, the first number that will give you is how many rooms. Let's say they have 10 rooms. Build an adjacency matrix, 10 rows, 10 columns. The fourth row has an edge to the second row. So in row 4, column 2, it's a 1. That's if you're using an adjacency matrix. If you're using an adjacency list, append 2 to the list in row 4. There we go. Yeah, that works. So BFS, the time complexity for it is m plus n, the number of nodes plus the number of edges. And then how many intersections are there? So there might be multiple, like here, like this is one, this is another, this is another, this is another. So each room has a range, right?
As much edges?
Huh?
The number of edges?
Yeah, so the number of edges, that does make sense. So the number of edges is m, but each edge has a minimum and maximum, right? So 2 values. So it's going to be 2m. And since we don't consider the ends, it's actually 2n minus 1. So here,
Consider what?
since we don't consider the ending, hey Demba. Yeah, since we don't consider the endings, we do minus 1. And then that converts everything. So we want to do, for all of these intersections, we want to do a BFS on just one value. So that means m plus n times 2m minus 1. I think you can, this is 5,000 plus 1,000, worst case scenario. This is 10,000. 50 million? Yeah, 50 million. Whoa, no, that's 50,000, sorry. So now we're working with 50 million only. Your NDA, they heard you? All right, take care, man. All right, it's fine, take care, take care. And then 50 million is much better than 10 billion. Cool, do you guys think you can code this up? Program it? Yeah, I don't know either. I know he gave the code. We have like the code in the video. But no, you should be able to, because you had everything right. You had the sorting right, and you also had the the intersections part, right? I totally believe in you. You got this.
I definitely.
If you do program it, or I have the link to this problem that I can send to you guys if it passes. And
Like a meat code? Is that a meat code?
so, yeah, that's a good question. For these competitive programming, it's actually not on LeetCode. It's on VJudge, which is much weirder. And if you look at the input, completely different from LeetCode. You know, that's probably why no one likes this or attends, because it's so different from LeetCode. It's much harder too, but oh well. We're smart people. We can figure this out. Don't worry. You good, Demba?
Not really, because I think I missed a lot of the class. Is this the only question you're covering today, or are you covering more than one question?
Yeah, this is the only one that he gave us
Oh,
for yesterday, so this is the only one I'm covering.
oh,
We can talk about it like after the live stream.
oh, yeah.
You had a question, I think.
Just like the code, like the solution to the marketing code.
Oh, you want the solution to it? Oh, I actually don't have it. Give me a sec. I need to look at his video because I did not write it down. Okay. Oh, yeah, we could have done that. That's fine. So let me just write it out in pseudocode. It's a pretty graph. I don't want to delete that. I'll delete this.
Sorry, can you use this pseudocode?
Yeah. So I haven't programmed it up. I probably should have done it.
Okay.
But it's pretty, right? Yeah, it's pretty simple. I believe it's simple. It's never simple, so let's find out. So the first thing, like you said, we want to sort it. The ranges. So let's call L is equal to sort R. And let's say R is our ranges. Now for I in range of 1 all the way to 2m. Reason we're doing 2m is because remember, each door has a minimum and maximum. So that means we have 2m values. Make sure this is lining up. Okay, yeah. Let's call this C is equal to PI. All right. L of I plus L of I plus 1 divided by 2. So it gets L of I is this one, L of I plus 1 is this one, and then divided by 2 gets us that middle value. Now with this middle value, remember how we said we want to test it to verify whether or not we could reach the destination? So what we do is, if BFF of C so if BFF of C, let's say this is in outside function that just runs breadth first search. I'm not gonna write that out because we know that part already. With this value, if it could reach a destination, so let's say this returns a Boolean, then we want to add the number of badges within that range. Okay. And then return answer. Yeah, actually that's it.
Wait, L, I don't really understand what L is. It's like a list.
Yeah. No, actually, it's going to be a list of just integers. Because this start and end is not going to be within a list.
So it's like 7, 20, and then 35, 35.
Yeah, 7, 19, 20, 35, 40, 60. It's just to have those values like that. Then we're taking the middle value between those intersections, running BFS on it. If we could reach a destination at this starting node with this badge value, then we know everything within that range would be accepted, and we can just add it to our answer, and then return answer. And that's it.
So how do you do this in like, I don't know how much time you have to solve it?
Oh yeah, let me look at the problem. Like the time complexity, that's what you're talking about?
No, I mean like, I don't know how much time you have to come up
Oh.
with a solution.
So that's a good question. How much time we have left? Or we have 3, 6, 9, 10, 11. So remember, this is part of a competition, the Southeast Regional. There's 11 problems. This is one of the problems. You're probably in a team of 3. The competition probably lasts, what does it say, 3 or 4 hours. So there is some pressure. And of course, you want to be the first one to solve it, because the first one to solve it gets the most amount of points. And you're on top of the leaderboard, and you can go to nationals and win prizes and potentially a good amount of money. So not a lot. I think the answer you're looking for is not a lot of time to come up with this.
Okay.
But yeah, the code is small. It's just the logic. I feel like the main thing about this problem was how to structure it correctly to find an efficient solution. Yeah, that's it. All right, let me sign off the live stream, and then but we can talk about it. Thank you guys for watching. Quick reminder, there's going to be a binary search night tonight from 8 to 10. It's a website kind of like LeetCode, but you can get in groups, and that group works on one problem, and it's kind of a competition. The first person to solve it gets like a gold medal. Second person gets silver, then bronze. Dembo, you know about it. You've been there. Was it fun?
It was, but let me see. I think I only got to solve like 2, 3 questions. All the other ones I didn't finish.
Yeah, it takes into account the skill level of everyone within the group, and then tries to give you the most appropriate question. Did you think it was fun though?
Yeah, it was fun.
Did you feel the pressure?
I mean, a little bit. The problem was like my internet connection was like really terrible, so it kept kicking me out of the channel and then back. So, but it was nice. I'll be there today for sure.
Okay, awesome. So yeah, 8 to 10 binary search night. It's an informal event. We're just gonna be on the Discord channel, in the Coding Dojo voice channel, talking and then programming. So hopefully you guys can visit that. But yeah, that's pretty much it. Thank you guys for watching.